Hello. Okay, everyone, we're about to start our next talk. You can see the title slide is here. I'm going to hand it over to you, Andreas.
Thank you. Hello, everyone. My name is Andreas Platschek. I'm working with OpenTech, and most of my working time currently goes into a project called Techniques.mp4. The title already reveals a lot about the project. We're planning to build a Linux-based platform that shall be certified to SIL 2, Safety Integrity Level 2, according to IEC 61508. And we're talking about MP multiprocessor system. We're not interested in single cores anymore. One big part of this project, or one big part that I'm working on right now, is to analyze the development process of the Linux kernel and of our other elements. And yeah, for that, we're using data mining techniques. And that's what I'm here to talk about today. So first, I want to give you a little introduction to the SIL to Linux MP project. The actual goal, I just said we want to have a certified platform. But the most important goal is not to certify one platform. The most important goal is to have a framework that allows us to certify all future platforms, future kernel versions, different configurations, and so on. And we want to verify our framework by doing the certification for one platform, for one use case. Yeah, it should be suitable for up to SIL 2. That's the target. And multi-core systems, already mentioned that as well. The open source elements that we want to use on the platform is the Linux kernel, glibc, busybox, and some smaller tools. And for today, I'll mostly focus on the Linux kernel because our assumption is if we can do this kind of analysis for the Linux kernel, then it will be doable for the other components as well. And even if it's not doable for example, busybox, which has a different development lifecycle, then we still have other options there because it's just a lot smaller. The methods that I'm presenting today are basically suitable for all kinds of pre-existing software. That's not restricted to the Linux kernel, but what we need as a prerequisite is the source code, of course, and the history in preferably JIT. And the target are software-intensive systems. So yeah, you already got that from the elements probably. So when you want to certify a software according to IEC 61508, you basically have three options. They are called Route 1, 1S, 2S, and 3S, where Route 1S is called compliant development. So basically, you develop a software from scratch. You, from the very beginning, follow the design life cycle as defined in the standard. So that's not an option here. Route 2S is called sorry?
Is it compliant, non-compliant?
No, it's by proof of previous usage. Proven use, yeah, thank you, Lucas. Yeah, it's called proven use. So that's only suitable for smaller software and not for a big chunk like the Linux kernel. And the third one, that's the one that we are using, is called Assessment of Non-Compliant Development, Route 3S. So basically, we have some assumptions. In this route, the first assumption is that we actually have a process in place that is defined. Of course, this process also has to be followed. It's not a problem if there are discrepancies between the actual process and the process that is defined, but we have to be able to assess the discrepancies, and if there is procedural defects, we need to assign mitigations to counteract those. The assurance that we want to give some examples is the qualification of involved people. So if you're in a company setup, it's very easy to say, okay, these people are working on the project, they have this training, they have this experience from previous projects, and to just write a small summary. But for the thousands of developers in the Linux kernel, that's not possible in this form. So what we're doing is to actually look at the development history of the developers and assign them a experience level, so to speak. Structural aspects of the organization, we're doing analysis of the reviewing process, of how patches get into mainline, of the integration, how many clashes were during integration into Linux Next, and so on. Then the methods and techniques used. So there are a number of methods and tools that shall be used if you are submitting a patch or before submitting a patch. And we are also doing an analysis if this has actually been done or to what extent it has been done. So for example, are the patches following the coding style, or is the coding style just for decoration? And we want to present the results in a quantitative manner, so we don't want to do qualitative assertions. We really want to put numbers on basically everything. So our concept for Route 3S is to, in first place, select those components that have no procedural defects. So if it's possible and there are multiple components that provide the same or similar functionality, then we try to select the one where we have better proof. So for example, if you have a file system and during the analysis it turns out that they didn't follow the process or part of the process, then it's easier to just select another file system than trying to do, I don't know, lots of review or I don't know what. Yeah, so assessment of the process. As I already said, we're trying to assess all the things from how patches get into the kernel, how many integration clashes happen, how reviews are done, or to what extent, and so on. Yeah, then we do assessment of the consistency of the results. And as I said, we want to quantify everything, and we also want to quantify the residual risks. More on this quantification will be presented in tomorrow's talk by Niklas. So I am kind of laying the foundation for how we are gathering the data. So the first point I had before was that a process has to be in place, and the good news is there is a development lifecycle in place in the Linux kernel. It's documented in the source code in the JIT repository in documentation process. And some examples for the content are how patches should be formatted, how the subject line in the patch should look like, how the body should be, what it should contain, how that patches should be signed off, and so on. It also defines the usage of the byte tags. It gives checklists on how and what you should test before submitting a patch, and it also helps you to find out where to send patches. So the good news is that we have a development lifecycle in place. So the next question is it followed, and how well is it followed? So, but before we go into that question, I have one more thing that I want to show you. I'm not sure how many of you know how a patch actually goes into mainline kernel. So I tried to picture this a little bit. So on the very top, we have the mailing lists, Linux kernel mailing list, and the mailing list for the subsystems. And this is where you send your patch. Usually, most patches are just sent per email to the mailing lists and to the subsystem maintainers. And from the email systems, the subsystem maintainers integrate them into the subsystem trees if they're okay. If not, they send back an email and say, hey, you have to fix this up and send another version of your patch so I can take it. So now the patch is in the subsystem trees. From the subsystem trees, we have a daily integration into Linux, into the Linux Next, into the integration repository done by Stephen Rothwell. So every day, about 240 subsystem trees are pulled, are integrated into this integration repository in Linux Next. And based on this integration kernel, a number of automated testing is done. So there are build bots, there's kernel CI and some others. They all have their specific purpose, their targets, their defects they want to find. And they are doing automated testing and send back warnings to the mailing list if they have some findings. So this is happening more or less continuously. The question is now, where do the versions come in? So you may have heard the term that Linus Torvalds opens the commit window. We're on the very left now. The mid-commit window is a period of about 2 weeks where Linus Torvalds pulls the commits from the Linux Next, from the integration kernel, and pulls them into his own JIT repository. And at the end of this 2-week commit window, he produces the first release candidate of the new kernel version 4.n. So that would be the leftmost green box, the 4.n-rc1. Now we're in a stabilization phase where patches are pulled in into further release candidates. Usually it's about 6 to 9. Now it's important to note that the number of patches pulled in decreases radically between RC1 and the others. So we looked at 4.4. I think RC1 got almost 13,000 new patches, while each of the other release candidates just got a few hundred, 300, 200, something like this. And at some release candidate X, Linus decides, okay, now we have a stable kernel, and he releases the new stable version 4.n. Now in this stable version 4.n, only bug fixes are integrated from this point. So from the mailing lists, only bug fixes are integrated into the dot releases 4.n.1, 4.n.2 to 4.n.y. And Y depends on if it's a long-term stable. This can be something really big, like 80 or 100. If it's a non-long-term stable, this can just be like 10, and the version is not continued anymore. And after some time, I think it should be about 2.5 months, 3 months, a new commit window is opened and the whole cycle starts over again. I'm not sure if there's anyone here who never saw a Git commit, so I just thought I would spend 2 slides on this. So basically, this is what probably everyone has seen before. We have a commit that is identified by a 40-character SHA-1 hash. The author is listed, as well as the date the patch was authored. Then the first line is a short description, kind of a subject. Then we have a body. And what maybe not all of you know, at least if you just know JIT, not every project uses this, are the last 4 lines. So those are those tags. I start with the bottom 2, it's the signed off by tag. I said the author has to sign off on his commit. So the author signs off to say that I'm aware that I'm now contributing to a project that is licensed to GPL v2, and I'm okay with this. So they sign off on the license basically. And of course that the work is okay. The bottom sign off is by the subsystem maintainer that everything is okay with the patch. Then the act by, so someone probably reviewed on the mailing list and said, okay, I reviewed this is okay with me. Or it might also be some other subsystem maintainer whose subsystem is impacted by the patch and saying, okay, I'm okay with this. Also very interesting is now the first one of those four, the fixes tag. So this fixes tag basically says, okay, this is a bug fix, and this bug fixes a bug that was introduced in the commit that is identified by this SHA-1 hash, or by the 12 characters of a SHA-1 hash. So this allows us now to go back and find out where and when this bug was introduced. And of course, the second part of the commit, the patch, the actual changes. From this, we can find out which files were touched, which lines in the files were touched, and so on. Now, when we started our,
So with regards to the commits that are decided for the stabilization for the versions, how do we determine which commits will actually get into the version that will release?
For the stable commits?
Yeah.
That's done by the stable maintainers, and they get it from the mailing lists. So usually they are just CC'd in the mailing list if someone thinks it's a stable bug fix, and then they will decide. So some of the problems that popped up when we started our adventure to look at this development life cycle. So our first explorations were simple command line one-liners and Python scripts trying to parse out data just to find out what's there, what can we do. But at some point we decided we have to do this differently, because we are a team of developers. We have also partner companies in our Silto-Linux.mp project. We want to make this data available. We want to distribute the data to the team members. We also want to keep it up to date. So ideally, if you, we don't want everyone to have to take care of that and keep their data up to date. So we want to do this in one point. We want to support this exploratory analysis. If someone decides to still do the command line one-liners first, that's still good, but still we want to present the data in a way so you can get a quick impression what's there or what might be missing. Cleaning data, that's an important point, and I have some examples of how we are cleaning data or in what ways we're cleaning data. But it's important to also do this in one place, because otherwise people could make it differently and versions would go, and data sets would go into different directions. We want to keep it consistent for all team members, so it doesn't happen that one posts a problem and it turns out it's just because his data set looks a little bit different. And we want, of course, to eliminate the processing overhead between the different analysis scripts. So we have different scripts that use the same data, but we don't want to grab and parse it out of the JIT logs every time, over and over again. So a few points on data cleaning. So we use the developer name as a unique identifier for the developer, as in real life. And here are some examples that we found in the kernel. While most of the things that we're cleaning up don't have the entertainment factor of these examples, we still want to attribute all the commits done by one developer to the same developer. So if there is a typo in the name, if there's a different lower upper cases in the name, something like this, then we want to catch that and attribute all the commits to the same developers. Another thing are the subdomains. We're using the email addresses to find out where people are working. Problem is, as most of you know, some companies just use different subdomains or different domains for different branches on different continents or countries or whatever. So we also want to clean that up so the affiliation can be found out properly. We're doing this to find out if there might be some dependence between the developers. Now we're coming back to the fixes tag. Before I just showed it to you and told you what it's about. Here is the actual definition of how a fixes tag should look like in a patch. So use the fixes tag with the first 12 characters of the SHA-1 ID and the one-line summary. For example, fixes, then the 12 characters and the summary. Problem is that, of course, also here there are some examples that look a little bit different. So we have references to bug 14662. I don't know, probably some internal bug tracking system at Dell. Or the next one, NB, seems to stand for Nokia bug tracking because it was submitted by some guy from Nokia, but I have no idea. If you know, please let me know. The third one is basically just text. Then fixes version 1.0. We're already starting to joke around that we should be using version 1.0 of the Linux kernel for SIL to Linux MP because it has been fixed. And the last one, which actually seems to be a good idea, is a reference to a bug tracking system. This example, bugzillakernel.org. But the problem is that we found a bunch of those, and some links are just dead. So these are just the bug trackers that are referenced by fixes tags. There may as well be others that are used somewhere in the body and not in the fixes tag. The length of the hash that was used, I tried to depict this a little bit. So it's varying from somewhere from 4 to 40 characters, but at least the proper value of 12 is the one that's the most common. This is really just for demonstration purposes. Actually, everything that's 7+ characters is not a big problem as long as we can resolve it in JIT. Usually it should be at least 7, I think. So basically, we're going back anyway and trying to find out which commit this is and get the 40 character hash. So that's not too big of a problem. Now, while these examples look like it's a bad situation, it's really not that bad. We have a total of a little bit more than 24,000 patches. And we only have 744 that could not be resolved, so about 3%. A big part of this were URLs and 18 CVEs. But there's also, for example, hashes that we can't resolve because it seems that the referenced hash is in some subsystem tree and just changed when it came to mainline.
Fixes that didn't contain a fixed tag at all?
Sorry?
Does that include the 3%? Does that include a fix that was actually not tagged at all?
There are much more fixes that don't have a fixed tag. So we know, we come to this a little bit later. Okay, so at this point, I want to show you what we actually, how our system looks like, how we distribute the data. Actually, this is still in a prototyping phase. We want to send this out to our partners within the next weeks. So what we're actually doing, so we have a web interface for browsing the data to get an overview. But for convenient use in R or in Python, we provide comma-separated values files as download. These are generated on demand. We keep it automatically updated. It's basically just a cron job. And it's extended as needed. So if someone, so last week we had the case that one of our team members came up with a new idea, what he wants to analyze, but there is some missing data, so we just extend it as we need it. So I'd like to give you a short tour. So this is our web interface, not very exciting. So basically we just have a list of our projects, and if we look, for example, into Linux stable, we get a long list of all the commits. Maybe one example where cleaning data is still in progress. We're working on the dates. It's very improbable that this patch was authored in 2037. But these are just the things that we also have, of course, some from 1970. These are easy to spot. It's harder if it's just an offset of 2 years, and that was 5 years ago. But we're trying to find ways to put numbers on how many patches actually have wrong timestamps. So we get a long list of the commits. If you go onto one of these commits, you get more of detailed information. The number of lines added, removed, files changed, directories changed, if it's a merge or not, who signed off on it, the commit message, and what I'm missing here, because this is a development server running on my laptop, and I just realized this morning that I forgot to do this. We're also running check patch on all the patches, so usually you would get here the number of errors and warnings from check patch. So for those who don't know, check patch is a tool that helps you to find out if the patch is compliant with the coding style. So we can also go at the developers list. So here we already get some numbers. So for each developer, we get the number of commits this developer submitted, or the number of commits that got into mainline, the number of signed off bys this developer gave, the number of reviewed by, act by, and so on. Going on the developer, now here we get all the email addresses that were ever used, not only to commit, but also to sign off, to review by, and so on. Resolved into companies where possible. And all the commits in this project that were done by this developer. And the fixes tag, so basically what we have here is the commit where the bug was fixed in the left column. The information we got in the fixes tag, we'll see this is important when we get an URL. Then the resolved commit where it was introduced and the time to fix in days. And if, for example, we have an URL, we try to resolve it. I don't have internet connection now, but if this is not a dead link, we just go there. Okay, so what's the general idea between this approach? The idea is that we have our input data. Currently, this is chit log and chit blame. We also take the Gimple output from GCC. I'll explain later for what exactly. We also use the cyclomatic complexity for all the functions. This is still in prototypes that I don't have in the web interface yet. And we put all this data in our database that is presented to the developers by the web interface and in the form of the comma-separated values data. And the developers can actually it's the statistics guys, can use this data conveniently in comma-separated values in their R scripts and produce some results, some statistical analysis. So let's look at an example how that looks like. So can you read this? It's very hard to read. So basically all I did was fire up R, do a read CSV of the URL to the fixes tags data. Now we have these fixes tags in an R data frame. And we can, for example, calculate the mean time to fix in days, or we can do a histogram of the time to fix. So it's really convenient. It's very simple to get from the data to to the actual analysis. So a second example I want to show you is a little bit more complicated. Here I download a bunch of CSV files. And what I do is I fetch for Weave version 4.4 to 4.4.1 all the stable bug fixes. So that's N, are the number of stable bug fixes. N fixes is the number of bug fixes that have a fixes tag. So now we come into your question. And the mean time of those tags, of those fixes with the fixes tags I took to fix them. And I'm doing this for all versions from 4.4.1 to 44. And I get a nice image on how so the blue line are all the stable bug fixes from 4.4.1 to 4.4.44. And the orange one are the stable bug fixes that actually have a fixes tag. So I think my colleague put a number on it. I think it's about 1/3 that has a fixes tag from those stable bug fixes. So we have this convenient situation where we actually know all those patches going into this dot releases are bug fixes. So we can compare and can find out how many bug fixes actually have a fixes tag for that part. And the other thing we can do, of course, a scatter plot, stable bug fixes over the stable bug fixes that have a fixes tag. And we can do a linear regression model, for example, and put the fitted line into it. Okay, I put all this code on the slides, so they are for download on the FOSDEM webpage. One other thing I want to talk about is where the Gimple output comes in. We want to do a patch impact analysis. So what we want to find out is which patches actually have an impact at our configuration of the Linux kernel. So all the data I looked at up to now was really for all commits for the kernel, but we are only interested in those that have an impact on our configuration. And the way we do it is that we build the source code and let GCC dump the Gimple output. From the Gimple output, we get all the files and the line ranges that are actually in our configuration. And we use this information to get from the JIT repository using JIT blame and JIT log -L, the history for each line that actually is in our configuration. And this way we can find only those patches that actually have an impact in our configuration. Okay, so that's already it from my side. A little bit fast. Yeah? Sorry? The Gimple, Basically, it contains the line information for each line that was used in your build. So basically, it just creates an output where you can see each line. For example, we know fs inode.c line 1947 was used. So from this kind of information, we can find out which lines were actually used during compile time.
Used means called or?
No, compiled. So this is done at compile time. This is really done while the binary is built. Yep.
Have you shared this information with the people at the Linux Foundation?
Sorry?
Have you shared this information with the people at the Linux Foundation?
Not yet. I know my colleague has contact with people from AGL and probably also from Linux Foundation. So we're planning to do this, yeah.
Maybe a related question to that. Is it reasonable to share this information with the Linux Foundation? Because once you tell them we measure you in a certain way, they behave in a certain way without.
Yeah. That's one of the things we're afraid of. Basically, before I said that we're trying to find out the experience of the developers. Of course, you can only do this in this project, and the developer may be very experienced in other projects, but we have some some limits to what we can do. But one thing that we're joking about is that people could start trying to get higher scores just for fun or something like that. But yeah, it may be a problem, maybe not. Yeah.
Or maybe some few words or an example of how this physics can help you in the certification stuff. So you, well, for example, yeah, you find out that, well, there is something broken and isn't compliant to your standards.
There are actually some examples in tomorrow's talk given by Niklas. Sorry. The question was if I can give some examples on how this will be used in the actual certification process and some defects that we have found so far. Actually, my colleague has some data on this tomorrow. He's doing analysis not only over the full kernel, but also on different subsystems. I think one problem you found was with FS.
Well, we've discussed a lot of problems, but a simple example would be, you look at the age of an average bug, so the average bug lifetime, you take the fixes tags, you correlate the fixes tag with a stable fixer to show that the fixes tag is a truthful or relevant representation of the typical bug in the kernel. The adjusted R squared there is about 0.96, so it's a very good fit. And then we have the average age of a bug, and now we can look at the average age of each line that is in our specific configuration. And from that we can estimate which ones are sort of new files or new lines and therefore have a higher bug probability, and which ones are very old lines that some of them are 12 years old with an expected rate of still containing residual bugs is much lower. So we can stratify the things. I hope that answers your question.
Yes.
Okay, but we can have longer talk about this later on. Okay, then thank you.